Yesterday we introduced the concept of uniform circular motion. We said it was circular motion in which the object was going around the circle at a constant speed. We defined a couple new terms: frequency, which was the number of revolutions per second, how many revolutions were made per second, and then we defined period, which was the seconds per revolution, how much time it took for one revolution to take place. Then we also talked about the speed, that constant speed of the object going around the circle. Today we're going to talk about two more terms, acceleration and force. They're not new terms, because we've seen acceleration and force lots before, but we're going to talk about them in a slightly different way. Uniform circular motion involves an object going in a circle at a constant speed. How can we talk about an acceleration, or a force for that matter, when an object is moving at a constant speed? What does a force do? A force changes speed or changes direction. An object going in a circle isn't changing speed, but it is changing direction. So clearly there is going to be a force, right, that's causing it to not go in a straight line. Remember we also said yesterday that an object going in a circle wants to go in a straight line. If we cut the string, it does continue to go in a straight line. Well, what keeps it from going in a straight line? There's a force. We call it a centripetal force. How can there be an acceleration, though? Here, the force thing kind of seems to make sense because it's not going in a straight line, but how can there be an acceleration if it's going at a constant speed? What brilliant Physics 20 student today has the answer to that question? How can there be an acceleration when the speed isn't changing? Jace, you got the answer to that one? How do we define acceleration? The rate of change of, close, it's the rate of change of velocity. How quickly the velocity is changing. It's not the rate of change of speed. It's the rate of change of velocity. Velocity is a vector, speed is a scalar, right? The speed isn't changing. But since velocity includes direction, and the direction is changing, the velocity is changing. So if acceleration is the rate of change of velocity, and velocity is changing, then there's an acceleration, even though it's not speeding up or slowing down. Does that make sense? We call it a centripetal acceleration. It's an acceleration, believe it or not, that points toward the center of the circle. It's kind of odd to think of that. An acceleration that points toward the center of the circle. But that's exactly what happens. If we have an object going around a circle like this, with a velocity, or with a speed, I should say, velocity that's counterclockwise, the acceleration at that point will be this way. The acceleration at this point will be this way, this way, this way, this way, this way. The acceleration is always toward the center of the circle. That's what the word centripetal means. Centripetal means center seeking. Now, we can't describe the centripetal acceleration by the old equation that we've had for acceleration, a is equal to delta v over delta t, because we can't really quantify the change in direction. And we need to be able to do that in order to use delta v over delta t. So instead, we're going to introduce a new equation that is specific to this centripetal acceleration. We're going to say A, C, centripetal acceleration, is equal to v squared over r. What does r stand for, do you think? It's the radius of the circle, right? What does v stand for? You guys all know this, right? What does speed stand for? The speed. It stands for the speed of the object going around a circle. A is equal to v squared over r. Notice the absolute values around the a. It tells us that there is a vector nature with it. There is a direction associated with this acceleration. We're just not going to get it from this equation, but that's okay. We don't need to get the direction from this equation because we know that it's always toward the center of the circle. If there's an acceleration, there's got to be a force. The centripetal force is the force that points toward the center of the circle. The the force that points toward the center of the circle. Right? F is equal to m times a. If there's an acceleration, there's got to be a force. In fact, we can use that equation, Newton's second law, to get the equation for centripetal force. If we replace a with the centripetal acceleration, then the centripetal force becomes m times v squared over r. Now, 2 seconds here, guys, before we take off here. Understand this, please. The centripetal force is not a fundamental force like, say, gravity is. Gravity is not caused by some other force. Gravity is caused by mass, but not by some other force. Friction is not caused by some other force. Okay. The centripetal force is. It's not fundamental. It's always the result of something else. Okay, as I swing my keys around my head right now, there's a centripetal force acting on these keys, acting toward the center of the circle. It's my hand, right? Okay? But something's got to cause it. Something's got to cause that centripetal force. It's my hand. Okay, when a car goes around a turn, there's a centripetal force. What provides the centripetal force? Friction. When the Earth goes around the sun, there's a centripetal force. What causes it? Gravity. When the electron goes around the nucleus of the atom, the electric force provides the centripetal force. So centripetal force is never a force on its own. It's always the result of something else. Does that make sense? Okay, we'll leave it there for today and do a few problems with this tomorrow, okay? Have a good night, everyone.